All right, so now we're going to take a look at reactions that can be carried out under different, and this may sound unlike an oxymoron, but under different constant conditions. So we'll take a look, first of all, at reactions that occur under constant volume conditions, and we'll take a look at reactions that can occur under constant pressure conditions. Take a look at constant volume first. So imagine for a second I have a container. This is the container here I'm starting with. It's got sodium azide in it, which has a formula NaN3. And then this container isn't allowed or cannot expand or contract. So the volume of the container is constant, in other words. What we find, and again, this particular equation is one in which the sodium azide decomposes. This is a decomposition reaction. It produces sodium salt, but then we get a huge amount of nitrogen gas. And this actually occurs in, is one of the reactions in airbags, when airbags deploy. Hopefully that doesn't happen to you, but in case it does, this is one of the reactions that occurs. The collision causes the sodium azide to decompose. It produces, a huge amount of gas, and then that's what inflates the bag itself. But in this case, we don't have a bag. We actually have this container that is very rigid. This is a rigid container. So the volume is not going to change. So the gas then that is produced, okay, so gas is now produced. Those gas particles hit the walls of the container and they increase the pressure, right? The force exerted on the area inside the container causes the pressure to increase. So what we would observe then is an increase in pressure when we're dealing with constant volume conditions. Now, if we were to detonate or perform the same reaction in a situation where we don't have constant volume, but we actually have constant pressure, so we're able to monitor or moderate the conditions such that we try to keep the pressure constant. So in this case, that would mean instead of having a rigid container, we actually have this piston here that is movable. So as the sodium azide here detonates, it breaks down, it produces a bunch of gases. The gases then will actually force this piston upwards. And as the piston goes upwards, then what we find is that there's an increase in volume. Guess what? There's a change in V. There's a delta V, right? Delta V here means change in volume when we have constant pressure conditions. And this is a very important, very common example of work that can be done by a system. It's called pressure volume or PV work. And that is done when there's a volume change. Okay, so change in volume would be delta V under constant pressure, P. And we define that then as being equal to the work being done being equal to the negative value of the pressure P times the change in volume, delta V. Okay, so again, sign here is important. Okay, W equals negative P times delta V. Why is W negative? Well, if we go back to our definition up here, work is being done by the system, right? It's causing the piston to move upwards. As a result, our W there is a negative value. That's why you see the negative sign. So P there is the external opposing pressure. And again, delta V is going to be the change in the volume of the container. Okay, let's take a look at an example. It says determine the work done in joules when a sample of gas extends from 552 mils to 891 mils at constant temperature against a constant pressure of 1.25 atmospheres, against a constant pressure of 1 atmospheres, and against a vacuum 1 liter atmosphere. Or it actually gives you a relationship that we can use. All right, so we need to determine the work done. So work here is equal to negative P times delta V. Okay, that's the equation that we've seen before. So what we would need is we need, first of all, delta V, our change in volume. And we have to look at this equation or the information that's given. It extends from 552. So that's where we're starting. That's my initial V. And then we end up at 891. That's going to be our final. So initial V here is 552 milliliters. Our final volume is 891 milliliters. So our change in V, change in anything, delta of anything, final minus initial. So we have 891 minus 552. So that's going to give 339 milliliters as my delta V. All right. And then here in part A, we're told that the constant pressure, so that's P, is equal to 1.25 atmospheres. So then what we can do is we can use that in our equation. So W equals negative P times delta V. Our pressure there is negative, you have negative 1.25 atmospheres. So ATM is atmospheres, that's unit of pressure. And then we have our 339 milliliters. Okay, so you will notice that neither of these two values is joules, but we were given a relationship down here where we're told that 1 liter times atmospheres is equal to 101.3 joules. Okay, so we do have atmospheres, but our unit, when we multiply these two things together, our unit there is milliliter atmosphere. So we actually need to convert the milliliters into liters. So we can do that right here. So for every 1 liter, we have 1,000 mils. Mils go away. So at this point, all right, my unit is a liter atmosphere or atmosphere liters. So you can multiply it in order. And then we would need to again take our conversion factor and stick that in. So then I have 1 liter atmosphere that goes in the bottom is the same as 101.3 joules. So liters go away, atmosphere goes away. We get joules as our unit. We evaluate that. That's negative 42.9 joules. Makes sense because it should be a negative value. Okay, the work is being done by the system on the surroundings. So let's take a look at how we can now interpret and make some mathematical predictions about what should happen, what shouldn't happen when we have either constant volume or constant pressure conditions. So we've seen that the work done is equal to negative value of the pressure times the change in volume. We've also seen that the internal energy of a system, the change in internal energy of a system is equal to the sum of Q plus W, right? Q here is the heat and W is the work done. So what we can do is we can do a simple substitution. We can take our W equals negative Q delta V, and we can substitute it for W in here. And then we just rewrite the equation. So the change in internal energy is equal to heat Q plus, now we substitute the negative P times delta V. And we simplify. So Q, we have two signs. That becomes Q, and then minus P times delta V. So that's our change in internal energy is equal to the heat energy minus the product of the pressure times the change in volume. So if there is no change in volume, so in other words, if what this means is if the volume is constant, so constant volume conditions, well, guess what happens? What is delta V equal to? If there's no change in volume, delta V, the change in volume is actually 0, right? So we can take delta V equals 0. We can substitute it back in here. Okay, so now I have delta U equals Q minus P 0. So I have P times 0, that's 0, my Q minus 0. So now my delta U is equal to, what is Q minus 0? Q minus 0 is equal to Q. So under constant volume conditions, where delta V is equal to 0, no work is actually done, and the change in internal energy is simply equal to the heat under constant volume, and we put the little V as a subject. So this is what happened under constant volume conditions. Under those conditions, the change in internal energy is simply equal to the heat released or absorbed by that system. What happens under conditions of constant pressure, conversely? Well, if we do our substitution again, like we did before, where W equal to negative P times delta V, we take that and we substitute it in here, or we end up with the same equation, delta U equals Q minus P delta V that we saw before. But now we can't simplify it. We can't take the delta V out because we don't have, or we do have change in volume. Here, the only thing that's constant is pressure, but this is not, the P here is not a change in pressure, it's just pressure, right? So we can't just say that's equal to 0 because it may or may not be equal to 0, depending on what conditions that you have. So we can't just assume that it is 0. So we have the same equation that we saw previously. We can rearrange this. We can solve it, for example, for Q, heat under constant pressure. So remove the Q, remove the negative delta P to the other side, we end up with a positive sign. So we end up with Q, heat under constant pressure, being equal to the sum of the change in internal energy plus the product of pressure times the change in volume. Okay, and that's an important equation to note, because we'll see here in a second how it is related to another term that we're going to see, which is a term called enthalpy. And enthalpy we abbreviate as H, and that is defined as the sum of the internal energy of a system, so that's U, plus the product of the pressure and the volume. V is the pressure, P is the pressure, V is the volume in this example. So that's the definition of enthalpy. Okay, the sum of the internal energy plus the product of the pressure and the volume. You will see, we're going to start seeing some more units now to describe pressure, internal energy, and volume, for example. Pressure, often we'll see Pascal, which has the same units as kilogram per meter times second squared. Volume in cubic meters. So that then if you multiply the pressure times the volume, what you actually get is something we've seen before. Okay, so if I have my pressure, 1 kilogram, or just kilograms, for example, per meter times second squared, that's my pressure unit. It times it by the volume, which is in cubic meters. Guess what happens? The meter goes away up here, this becomes meter squared. So I end up with then the unit of 1 kilogram meter squared per second squared. And if you remember, you've used this relationship before, that is the same as going to be joules. That is the unit of energy, right? So enthalpy then, we use the same unit, joules. Important to note, we've seen already internal energy is a state function. Pressure volume we already defined as a state function. And enthalpy, our new term, is also going to be a state function as well. So for any process, the change in enthalpy of a system, right, if you think about it, so if I have my H being equal to U plus PV, if I have my change in a system, I just insert the delta sign. So delta H equals delta U plus delta times PV. Okay, what we can do now is we can simplify this, right? If the pressure is constant, then there isn't a change in P. P is just a value, it's just P, but we do have delta H then would be equal to delta U plus P times now delta V, right? So if pressure is constant, we don't need to put the delta in front of P because it's the same. And what we can do is we can rearrange this. We can solve this then for delta U. Okay, so rearranging this equation, if I put the delta U, keep that on the right side, then delta U is equal to delta H minus P delta V. And if you recall, right, from up above, you saw the heat under constant pressure is equal to delta U plus P delta V. Okay, and what I can do is I can take this, what delta U is equal to, and substitute it into this equation for delta U. Have QP now being equal to delta U, which is all of this stuff. Have delta H minus P delta V, and then I still have this remaining here, plus P delta V. Guess what? These two things here are going to cancel out. Negative P delta V plus positive P delta V, they go away. And I end up with heat under constant pressure is equal to delta H. So what that means then is that under constant pressure conditions, which by the way is what we do in the lab, or in most cases, most instances, we work under constant pressure conditions. So you work in the lab, the pressure doesn't change, right? It's the pressure of the room, it's atmospheric pressure, that stays constant. What we find is that the change in enthalpy, so delta H now, is simply equal to the heat change, or the heat under that condition as well, right? So it makes it easier to measure or to calculate or to determine delta H, the change in enthalpy, simply by measuring the heat. Under constant pressure conditions. And again, that is something that we do under normal circumstances. So we've done a little bit of a derivation here of this relationship. And in most Gen Chem 1 classes, we do talk about this. Now, again, there's not a whole lot of chemistry involved in this. This is a little bit of manipulation, mathematical manipulation, algebraic manipulation, and substitution. This really isn't anything chemistry intensive. We'll get to that in the next section. So when we talk about enthalpy, right, we can simply define it as being heat changes under constant pressure conditions. And it's much easier to measure heat changes, to determine heat changes, than trying to determine internal energy and all that stuff. We can make this equality, make this relationship work for us to determine changes in enthalpy. So one of the important changes in enthalpy that we're going to see, and again, in chemistry, we're going to be talking about chemical reactions, is the enthalpy of a reaction. Okay, and that is our delta H, enthalpy for a reaction, delta H, and I usually see delta H Rxn for the reaction. So it means is simply the difference between, again, okay, delta of anything is going to be the change in the final minus the initial. Okay, and specifically now, the enthalpy, the final, whatever the final is, minus the enthalpy of the initial. Well, guess what? In a chemical equation or chemical reaction, what do we start with? What do we end it? Well, we start with the reactants. We end with the products, right? So the reactants here are our initial. and then the products are the final. So what we can say is that delta H for a reaction is simply equal to the enthalpy of the final, which is the products, minus the enthalpy for the reactants. It is very difficult to determine strict enthalpy values, but it's a lot easier to measure enthalpy changes for a process. And again, this is assuming that reactions in the lab occur at constant pressure, and they often do. In 99.9% of the cases, they do. What we're going to see is that we can now tie in some of those earlier terms that we saw. Delta H, the change in enthalpy, is positive for endothermic processes, right? And this is where heat is absorbed by the system from the surroundings. Whereas delta H is negative for exothermic process, where heat is released by the system into the surroundings. Okay, so now we're getting somewhere with this. You know, we introduced these terms early on. Now we're trying to tie them back to actual values that we can measure and terms that we can define. So enthalpy changes, that's what we're going to focus on. Delta H values, positive for endothermic, negative for exothermic processes. We can take those values now, or what we know about them, and we can bring them into, we can now relate them to our equations. And when we tie in those thermochemistry, those thermochemical values, we come up with what are known as thermochemical equations. Now, this sounds very complicated, but it is actually very simple. All a thermochemical equation is telling you, in addition to a normal chemical equation, it is also going to tell you what the delta H of that reaction is, right? So this here is the enthalpy of reaction for this particular process. I'm going to put the Rxn here at the bottom, because it's always good to define what the enthalpy is that you're talking about. In this case, it's for this reaction. Okay, so in this example, going from a solid H2O to liquid H2O, this is a positive value. Okay, and your enthalpy for reactions are often given in kilojoules per mole, so heat energy per mole of the reactants that we're looking at. This is a positive value. That means it is an endothermic process. That means heat energy is required. It's absorbed by the system. And think about what's going on here. We have solid water. That's ice turning into liquid water. Okay, obviously, for ice to melt, the ice has to absorb heat energy. That's exactly what this is telling you. Okay, so we can represent that in an enthalpy diagram, which is shown down here. Very simple diagram. We'll see more examples of these down the road. And that just shows increase or changes in enthalpy on the y-axis. We have delta H here, that's change in enthalpy. Obviously, zero down at the bottom, increasing as we go up. In this case, we're starting off with H2O solid, that's my initial. And then we end up with H2O liquid, it's final. So obviously, I have a bigger value for enthalpy over here. And my initial value is a much smaller value. So the difference there, delta H, would be a big value minus a small value, which would give me a positive value for delta H. In terms of one that is in the opposite direction, so here we have the combustion of methane that you find in your gas stoves or in the Bunsen burner in a lab. Okay, so the CH4 reacts with oxygen to produce CO2 and H2O. The delta H for this reaction is negative 890.4 kilojoules per mole. Negative value for delta H tells us it is exothermic. Okay, and what this means in terms of our enthalpy diagram is that the reactants are higher enthalpy than the products. Right, so now I'm starting over here. This is my initial. And then I end up with the products down here. This is my final. I'm going this way. My final value is smaller than the initial value, which is larger. So obviously, if I have a small number minus a large number, that's going to give me a negative value. Yeah, it's exactly what we see right here. So when when we show these delta H values right next to our balanced equation, that is simply what a thermochemical equation is. Now, the thing about enthalpy is that it is an extensive property of matter, meaning it depends on the amount of, of that thing. That is in contrast to an, let's say, versus an intensive property, which does not depend on the amount, right? So for example, the density of something is intensive. It doesn't matter how much you have, the density of that thing is always going to be the same. Enthalpy, though, is extensive. It does depend. So for example, if we have the reaction of liquid or the conversion of liquid water into water vapor, that is an endothermic process. It requires 44 kilojoules per mole. If I have 2 moles of liquid water, when I convert 2 moles of water vapor, it actually takes twice as much energy. And if you think about that, okay, that is going to make sense. Right? You have more of it, it's going to require more energy to vaporize it into the gas phase. So enthalpy is extensive, and that's important. Depends on the amount. We're going to tie that into some equations down the road.